before you're doing this, there's a control exchange taking place, which then has authentication. So that's your password. And that may be the best way if somebody wants to map your account with an IP address to have them DHCP assignment based on that. See, there's an authentication taking place. But this is all worthwhile. Yeah, there's a lot to study. Once you get the lower layers become more interesting because we know now a lot about how IP works. Yeah, but it's not, we're just going too deep. We're just getting into really a very rich soup of terminology and technology. Anyway, so that is what your home router does. It's DHCP server to the inside, DHCP client to the outside. It also performs this translation of addresses from here into something that maps into 64321. This is the network address translation file. Yeah? So these are the three pieces which you put together in lab number 7. So if you're doing this is essentially you can now, if you're repeating the exercises that you do in the lab, in lab 7, you can turn any Linux box into a home router, and it will work well. Yeah, you just need 2 Ethernet interfaces. One Ethernet interface goes into your cable modem or in your DSL modem. The other one goes into your whatever switch you have or wireless hub that you have. That then does the Wi-Fi part of the inside. This is pretty much all that is necessary, and you can configure it using the commands of Lab 7. If you're having Linux, the DHCP, these are just clients that you start and servers that you start and reconfigure. It's relatively easy. For NAT, there is this is really deep down. You're going in there and changing the IP forwarding functions. So there are utilities, commands in Linux that you can use to change kind of these NAT rules. Yeah? This is called IP tables. It's just sweet of command. That's it. So you can change. You can save $30 by putting a $1,000 PC there. Yeah. That's what you learn. All right. But it's demystifying the entire process. Yes.
Will it perform better than a normal router?
What the performance? Yeah, 4 megabytes. Yeah, you can carry it. You can probably use your smartphone there as a home router. That's something. Yeah. So a PC could dealing with a gigabit per second on this side. No problem. Yeah, you can put a gigabit, but your subscription will increase. Yeah, how much do you have right now? 24 megabit per second. How much do you pay?
42.
42. Well, go to a gigabit per second. You multiply by 20. That's what it will cost. Yeah, roughly. But then your home router will not make it. The cheap Linksys router. But your PC will.
So if you don't have a static IP address and using that dynamic address that we get assigned, can we do a remote desktop from anywhere else outside?
To get applications where there's a lot of things that you can do. In the end, this is all just translation rules at the level of IP addresses. Applications are running on top of this. Depend on the IP addresses. So one has to look at what the application does. And we'll see in this lecture that some applications you can run over a NetBox. For some applications that are the NetBox is aware of the application, and it does things. On a very simple level, if you're using the ping command, ping does not use port numbers. You're pinging, you have 2 IP addresses pinging out. They now get shared IP address. The ping comes back. It's now being mapped into what? There's no port number to map it to, but it comes back to the right. It goes back to the right to the pinging host. Magic.
You got it.
If you're sending,
It just knows. Maybe Cisco knows it. Yeah, so there is some awareness. So how is that done? That's a very nice exam question always. Yeah. How is this done? Because you know it. That's easy. Most people don't know it, so you have to think about how is it done. So it's just pretty much looking at the IP packet and you know just doing this mapping. What can you do? And what field do you have that identifies what distinguishing feature do you have in an IP datagram that this box needs to memorize so it can perform the mapping back?
is that the name of the computer sometimes? Name of the computer?
At the IP level, there are no names. There's only IP addresses. It's like you have no name, you just have social insurance
So
numbers.
NAT is only on IP, doesn't talk to
The NAT is only IP plus with ports. So it's a little bit of port numbers. So it mixes, it essentially makes the port number part of the machine address. So it steals a little bit from the transport layer, but it's completely done.
The other thing is, if it's dynamic IP address, how does the ISP keep track of how many bytes you use?
Well, they have your account. You're logging in. The question was, before you always get the same IP address, then they know, yeah, so they keep, but you're logging in at the lower level here. That login is being sent. You have, so everything that comes over this logged in connection, that's yours. And you're mapped to an account. And it's not done to the IP address, it's really mapped to an account. When they log traffic, they have to then make the connection between your account and the IP address. And then if you're assigning different IP addresses, you have to have some mapping, so if you have something static there, it's easy. But static IP addresses means you have for each customer a separate IP address. That is also something where you may want to do NAT. What you can actually do is, this here could be another layer of NAT. You can nest NAT boxes. All right, let's get started. And look, it's very close. So I want to have these discussions. It strikes close to home. Once I go into the slides, it's just just stuff, material, but relates to something that you're experiencing on a day-to-day basis. And these are exactly what you want to do. You want to relate it to your own personal experience. Okay, network addressing space. So there's the concept of a private IP address, private IP network. A private IP network is your home network. It's essentially a network that is not directly attached to the public internet. Directly attached meaning the addresses here. You need to have a box. There's a box in between. You could not connect this home network to something directly connected on the internet. Now that's a private. In a private IP network, you're just on your own. You just create your own address bubble. You can use any IP address. Your home router, you could send here in your home network. In your home network here, you can assign address, you can have your ECE server allocate addresses that are valid in the public internet. No problem. What's the only problem?
It's not in the DHCP range that you are allocated to?
Yes, so if you're using here 128.100, 11, 128.100.3.1, we can do this, yeah? Let's have your DHCP server allocate 128.100, which are UFT addresses. Works like a charm unless you want to access something in this address space, because that traffic will not leave, it will be local to this network, yeah? So your net router will keep it local. That's something that we recently did for a So you can play with this. You can make your life very easy. I was organizing a conference, and a down from you saw these little notebooks that you have from that conference. Yeah, so I organized it in downtown with 500 people. Big event for network research, biggest event possibly. And so we have for registration desks and for computer room. You know, I got my printer from my office and from my lab. We got it down there, and then configuring my IP address on the printer is a big pain. Yeah. So what we did is we essentially created a private network, where we just used in a private network the addresses that these computers have, which is perfectly fine. And what we then also did, they used then a second interface on the the wire interface was for the printers and using the addresses that they had anyways, so they didn't change that. On the wireless interfaces, we then went into the network there that was going to the hotel network. This was a network set up by Cisco Network, so they came in with a guy who set up a wireless infrastructure. And works fine unless you wanted to access, if you of course wanted to access it. I could not telnet into a computer in my office from any of these machines. So I play with this.
So if one of those machines tries to access 128, 100, 111, for example, the router is not going to know whether it's going to be a local one or the URC.
Well, it's just you're making your decision here. You're not saying this machine, if it has something, it depends on the sub. If you're using 24, let's suppose you're using 16, as a subnet map. Your local computer makes the decision, this destination is local. It doesn't send the packet to the router. This machine makes it. Something we learned in the first week. The important decision is something on the local subnet or not. Perfectly fine. Yeah, but other than that, it works. If you don't have to go to this network, it will work. Yeah, it's just when it collides, things happen. The IP address in a private can be signed arbitrarily, not registered, and not guaranteed to be globally unique. You don't have to just assign them the way you want to. If you have different networks, that's why each Linksys router can have, the same address. The private network addresses, these are the non-routable addresses in this range. So there is this range 10. This is actually the old address of the original ARPANET. That is the beginning of the internet, the first network. The first networks, the first ARPANET that was set up, the IP address given to it is from this range. It was retired sometime in the late 80s, early 90s. And this is the address that was then the Class A address. That was given them, was released and made experimental. Then there is Class 2 address, and this is here a whole bunch of Class C addresses. Class B address, and a whole bunch of Class C addresses in this range. And that's where the numbers are from. So this is how your private picture looks like. Pretty much do it. You have your private networks with addresses here, 10.0.1.2, 1.3, 1.1. And here you have kind of the same addresses, and that this should be a different private network. And then you have public addresses, the routers that connect the private network to the internet. They have public addresses because they connect to the internet. They must have public addresses. This way, so what happens is to have these, allowing these machines, H3, to access H5. There's some translation function that has to take place. That translation function is network address translation. It's the translation from a public address into private addresses, and from private addresses into public addresses. And it's in that generality. It is not network address translation does not mean that there is only one IP address out here. In fact, many users of network address translation have multiple. The router that has, there is a whole bunch of there are multiple addresses that are available, like subnets that are available as public addresses. So the home router example, where you have multiple IP addresses being shared, one IP address being shared by multiple computers, and the resolution is done with port numbers. That's only one of several uses of network address translation. Network address translation is relatively recent, in 1995. It's not recent for you But it's reason enough that I know the person who did it. That's just, network research. He was here at this conference. And it's not a big intellectual achievement at the same time. He would say it's not one of his. It's just something that is, if you do something and then it's used by the entire world. Network average translation has done, without network average translation and without DHCP, we would all be running IP version 6. We had different labs. Not talk so much about running out of address space. Not talk about this at all. Network average translation and DHCP are the main reasons that the internet within its version 4 is still moving along. Yeah? And you can push network average translation, because you can do it in multiple, you can do it more than once, can really help to preserve IP addresses. Okay, so network average translation is a router function, very important. It's something that is implemented on a router in the IP module at the IP layer. It's a function whereby IP addresses in datagrams are exchanged at the boundary of crossing of private networks to the public internet. With NAT, hosts on private networks can communicate with hosts on the internet. Sometimes also the other way around. Depends on how you use it. This is a little bit repetitive, kind of a little bit more technical. NAT is run on routers that connect private networks to the public internet. We've said that. What it does is it replaces the IP address and port, a pair of the IP address and port, with another pair. So this is the basic operation of NAT. There is a table, that is the network address translation table, that has a private address mapped to a public address. If that has taken place, if this is a computer here, this computer here has a private address. The computer here has a private address, not the NAT router. I call it NAT device. But it's a function that is running as part. It must be a NAT device is also a router. The host here has a private address and a public address. The private address is used to communicate with other machines in the private network. The public address is used to communicate with things on the public internet. The NAT device has a translation table. If a packet is coming in from the private address hitting the NAT device, it looks up the private IP address, replaces the source address of this packet with the public address, and then the packet has this IP address. The host is then responding with a public source and a destination address. The NAT device is then at the boundary performing the reverse translation, sending then the packet back with destination 10.0.1.2. This is a basic function. NAT does not mean that you share IP addresses. It means exactly this. A host has a private and a public address. The NAT device performs the translation between the two. There are four main uses of NAT. One of them is to pool IP addresses. Second one, which means an organization has 50,000 computers, but only 16,000 address block, but 16,000 addresses.
My question was from the previous slide.
Yeah.
So does each host actually know its own public IP address, or just knows its own private IP address?
The host only knows its private IP address.
So the router will actually do header manipulation to change that, so
That's the NAT device performs manipulation of the IP headers. It exchanges, the NAT device replaces IP addresses and possibly also the port number. That's correct. The host only knows its private address. The host on the public internet only knows the public address. The NAT device performs the translation. That's the only device that needs to be configured. It's the only device that is configured.
So
Yes.
there can be multiple public addresses in a network for multiple users. Multiple hosts.
Yes. So this address can belong. Let me go into the example because that's exactly what other users of network. Let's talk about pooling of IP addresses. The scenario is this: that a corporate network or an enterprise network like U of T has many hosts but only a small number of IP addresses. So what you can do is you can manage the enterprise network as a private IP address. Then most of the traffic is internal. You're then configuring the NAT device to perform the translation with this 50,000 private IP addresses to, let's say, the 250 public IP addresses. It's like a pool. Think about like DHCP. There's a pool of 250 public IP addresses. If somebody from the inside makes an access to the outside internet, you just take you take an IP address, public IP address from the pool, put it in the network address translation table, and so it then can communicate with the inside, and the outside can communicate to the inside. Let's see how this works. So, private network, private addresses. The NAT device, here's the NAT device, here's the public IP address. This is the hosting on the public internet with the public IP address. The corporation here, which is running the private network, has a pool of IP addresses. You see here, it has here 30 IP addresses. Huh?
0 is 0.
Yeah. Can you use 0?
No.
Did I say something wrong?
No.
What was your point?
No, I have no.
You see, this is, it's actually good that it comes to learn something here, yeah? 31, now you know it's 30. Completely used to this now, yeah? Because it's yeah, these things are not obvious, but now you know. That was my point, yeah. 30 of the, I don't know why I picked 30, that's just a strange number. Now, if a host 1 initiates, contacts the internet with going out to the internet, the NAT device creates a row for host 1 and it takes a public IP address from this pool. Yeah, I can't do it with this strange mouse, but normally I should be able to. I should not try, but I can. 12.10. No, that number I can't do. Let's say X. Yeah, so this entry, I can't even do the X. It creates an entry X. It sets what it does. As you can see, it's here. It takes 128.143.71.21. That's the entry that is in place. Now what happens after this entry is created? Host 1 and host 5 can communicate perfectly. It has to happen that H1 has to contact H5 first. It doesn't work that H5 can contact H1 first. So the contact has to come, the client connection has to be always on H1 side. But once the connection is established, host 5 can send packet to H1, no problem, in both directions. Alright, what else is there to know about? Yeah, so the NAT device is managing this pool. Okay, so what happens here, this binding is kept in place for some time if and public, so the NAT device has to monitor if a binding is still in use. If a binding is not in use, the address will then be released to the pool. Yes?
What if a host destination, so what if the private network has a destination address that is private to the network but also public? So how does the host distinguish between the two? Let's say it's 10 for...
there should be no conflict between private and public.
There shouldn't be any conflict?
There cannot. These private addresses have no meaning in the public internet. They cannot be used. They're non-routable addresses. And, you know, if you're using public IP addresses in the public internet, if the private network uses something that has meaning in public, the private, you know, if you're doing the outside, network will never see it. If you're assigning inside, if I do something, 128, 100, these kind of shenanigans are not visible on the outside. Outside, you only see the public IP address.
So there's only a specific range of addresses that you can assign to public?
Oh, it can. It's the addresses are the addresses that are acquired by this corporation.
Okay.
You get this from your ISP. You get an address block of 30 addresses.
And these blocks cannot be used by the public internet?
These are public addresses, yes. These are public addresses.
Okay.
They are acquired from the public IP address space. These are not random, arbitrarily selected. They have to be acquired from the service provider of this private network. Or you have to, you know, if it was U of T, if U of T would do such a thing, it would go directly to the registry.
Okay.
ARIN, the registry for North America. Yes.
So before 1995, you had 5 computers at home. Each one would have its own unique IP address?
Yeah, you didn't have home networks. I mean, people like that, yeah. You had to dial in. 1995, getting a dial-in modem was a big deal. And it was your phone line, your computer connected. Yeah, until you probably will still remember it and have never used a laptop with a phone connection. That was the only way to get internet access from home. DSL came about in the late 1990s. Cable modems around the same time, mid 1990s, coincides with this. Now, once you have this, you start running a wireless network. My first home network was a wireless router that was going into the phone. Because where I lived, there was no high-speed networking, and there was no cable modem and no DSL available. So I pretty much had a home router that was a modem. Yeah, and this whole setup of this home router and 2 wireless Ethernet cards set me back $1,000. Yeah, that was then. Yeah? So this, yeah, so that's, but it's no coincidence that this does not happen. So people did not have home networks. No, actually, people did. But then, yes. What people did is they configured there was no Wi-Fi, yes, you have to think about that. So everything was Ethernet, right, on the inside. What they did is the computer here was the computer that you dialed in with. You configured it. There was also no Linux. There was FreeBSD. So you then had to configure your router using FreeBSD or something like that. But you could do this too. But very, very few people. I'm talking like professors in the computer science department where it's got a second computer connected, and that is as far as it went. Yeah. All right. Good. The second example is very similar. It has to do with using NAT to make it easier for a corporate network, again, private network, corporate network, enterprise network, to be flexible with their network service providers. this is the problem with network service providers. Let's say U of T, suppose it would get its IP addresses from Bell Canada. If it now wants to change to Rogers, all IP addresses will need to be changed because now we have hierarchical. The address block would be acquired from the service provider. If you change your service provider, you have to change all IP addresses. Which means that all computers have to be reconfigured. All DHCP servers have to be reconfigured. You can avoid it by using NAT. That use of NAT goes like this. You're just using private IP addresses on the inside. The network address translation provides the mapping, and this can now be a one-to-one mapping of private to public IP addresses. So each computer in this setting has a public IP address, which is derived from an ISP. The ISP1 allocates the address block 128.143.71.021 to the private network. So the public IP addresses are then all from this range 128.143.71.21. This is the public address. So at one time, the organization decides to switch from ISP1 to ISP2. If you have used NAT on the inside, no computer here has to be touched. They continue to use the same private IP address. The only thing you have to do is to change the mapping. Yeah? It's a big time saver. And so you're decoupling the address assigned within the organization from the actual numbers that are being used. It's pretty much protecting yourself from a change of address. Very convenient.
I have a question.
Yes.
So can one private address have multiple public addresses mapping?
Well, in principle, that is possible. Yeah, you could have multiple entries here, but the NAT device here. Let's see. Actually, I think that is possible. Yeah, it does not cause confusion. In principle, it's not a good idea to do this. What you would have, you have one row 10.0.1.2. 128, 195, 4, 120, and then you have a second row.
With the same private address?
Same private address.
And different public address, I mean.
Different public
like say before, like when you talk about the autonomous system, you said U of T is part of the National Research Network, and also we have another provider to provide us some sort of carrying other sort of data other than research data. So I think we have two different service providers,
good.
Right?
Yes. Very good point. U of T owns its address block. So you remember when we went to the database and looked up the address block of ISP and ARIN? So U of T owns that address space. So it does not, in fact, U of T does not obtain its IP address blocks from its service provider. Yeah, this concept of obtaining the addresses from the service provider is a consequence of classless interdomain routing, and where you have this hierarchical address blocks.
Yeah.
Large ISPs giving address blocks to smaller ones and to smaller ones, which creates opportunities for route aggregation in the network. But what you say is, suppose, and that's actually the case, suppose U of T would do this. What would happen is then that U of T would so Eric, it's created quite a situation. Suppose you have two ISPs. U of T has two ISPs. It owns its own addresses, so no it doesn't obtain its IP addresses from spaces. But if you have multiple service providers which allocate to you IP addresses. Now what you want to do is you have one network that is used for research purposes, the other one being used for vanilla internet traffic. If you obtain IP addresses from those, then you have two options. Now you only have one option. You need to actually run that in here, perform a dynamic address translation here that looks at the destination of an outgoing packet. Based on its destination, it provides an assignment either from pool 1 or to pool 2. You see this? So that is, you see that what I'm saying? Because then you would get an IP address that has meaning, is routable in these.
So if the data is going to research, it's pick from the pool 1, yeah.
But you see this concept of having multiple entries here. If you have a rule of using one over the, if you flip them between the two, you're creating, it's just like you're in the middle of an IP address. You're changing in the middle of a TCP connection. You're changing your IP address.
Yeah, it's kind of. So
it
that's
could still work though. It could still work because it will probably not work. Yeah, but there is no reason. It's just something you don't do. You don't change your source address in the middle of your login. Yeah, that can be a lot of mischief. Think about security. Yeah, all of a sudden your bank is saying, oh, the source IP address has changed. Never mind. We're still active. That's probably not a good idea to accept. Yeah, but in principle it could be done. From the IP perspective, you just have to be very vigilant about it. In other words, it's not a good idea to do. And if you're having a fixed rule, always pick the first one, then why did you pick the second one? Yes?
Could it not be used for redundancy purposes? Say the first IP goes down, then you use the second entry in the table.
Well, I don't know about that. A redundancy. You have one network as backup.
I guess, yeah, it's the same private address.
Well, look at this. This is just a table. They have commands that change these tables. So, you can open a company with a script. It says, well, I have an instant change over IP address, fail-proof over, I can guarantee you 50 milliseconds after the ISP goes down, you will start be able to use your second ISP transparent to the network. Yeah, and then you would just have a script that changes that table very quickly once you have knowledge. See, it looks very powerful at the application. It's something very simple. All right, there are two more examples of net. I take my time here because we can relate this. Yeah, so I don't want to just go through the slides. One of them is IP masquerading. The other one is an interesting one. It's the reverse use of net, where you're using net for load balancing between servers. So that's used for front end for server farms on the internet quite a bit. If you have a single IP address being published on the internet for a server farm, and then you're load balancing between them to do your web commerce, and that can also be done by net. All right, I'm going to see you tomorrow. Tomorrow we'll return the quiz.